This video is showing you how to simply design matching networks like an L match and a pi match for aerial tuning units or transmitter matching without having to use a computer to do what is really a simple task. So I'm going to start from the very beginning of the story, from the very beginning. So this is an alternator or a source of alternating current. It could be a transmitter, of course. And what I've done is I've connected to it a capacitor. Now at a certain frequency, a capacitor does oppose the flow of current. You can't get an infinite current through it because it has an impedance which is resisting the flow of the current. It's not quite like a resistance because no energy is actually burned, it just stores it temporarily, stores the energy temporarily, but this impedance of a capacitor is called its reactance. So for instance, if this was a 1 volt generator and this had a reactance of 1 ohm, then we would find 1 amp of current flowing. So that is really the basis of a lot of this thing we're going to talk about on matching networks. Now this is the case where we have, I've shown 2 capacitors here, but these are imperfect capacitors. This one has got some resistance in series with it, it's just built into the thing, so actually it's not a very perfect capacitor. It loses energy when we, if we put energy into store and then take it out again, we don't quite get it all back. This one has got a resistance in parallel with it. Also it loses energy. Now this, these 2 circuits for alternating currents can be made exactly equivalent, and if they were if each of these was in a black box we couldn't tell which was which. So the ratio of the, if this has got a certain value of reactance, say 100 ohms, if we put a 1 ohm resistor in series with it, that's 100 to 1 ratio. So it's quite a good capacitor, but slightly lossy, and we say it has a Q of 100. The Q, quality factor, is 100. That's 100 ohms of reactance, 1 ohm of resistance. Now this one, this is 1 ohm of reactance still. But to lose just that little bit of power, this is a very high resistance, and in this case it's going to be 100 times higher. So this would then be, if that's 100, this is 100 times higher than that. So actually it's 10,000 ohms, a very high value. And this also, if this is in a black box, it also has a quality factor of 100, a Q of 100. In this case, this resistor is 100 times greater than the reactance of the capacitor. So we can use a simple formula to relate the 2. Now we need to be able to relate these 2 capacitors. This is the fundamental thing about matching networks that we're going to do now. So remember I said if this is 100, this is a good capacitor, we'll say that's 1 ohm. This is the same capacitor, it's in a box. We might think there's a resistance in parallel, in which case this is 100 times 100, that would be 10k, 10,000. So to relate them, this is the simple formula. The parallel resistor over the series resistor is approximately equal to Q squared. Now remember I said that Q is the ratio of these 2. It's the ratio of X to R. X reactance over R is 100, that's the Q. Here, R over X is the Q. So this is the simple way. Parallel of a series is Q squared. For most ATU and network designing, especially doing mental arithmetic, that's good enough. In some cases, if the 2 resistors happen to be close in value, we have to use an exact formula. This is the exact formula. Parallel of a series is Q squared plus 1. But you'll see that Q squared usually is a big number. So it's only when the 2 are very similar. For instance, if you're matching a 50 ohm transmitter to a 60 ohm load, that type of issue, it comes up. So this is, I've just depicted a matching network that we're going to use. So in this case, this antenna here, it's a 12.5 ohm resistance, and the transmitter we're looking to get 50 ohms here. So this is giving us a 4 to 1, going this way, it would be a 4 to 1 step up. We call that the transformation ratio. transformation ratio, that's the starting point. So the transformation ratio is 4. And then the working Q of the reactances we're going to use, that's the next thing to get. Simple. The Q squared is the transformation ratio. So the Q equals, that's the square root of the transformation ratio. Q is 2. Q is 2. So when we start looking at our network, we want everywhere to define a Q of 2. This is the antenna, which was 12.5, a pure resistance. Now to produce something having a Q of 2, we're going to intentionally put a capacitor in series with it, and we want this combination to have a Q of 2. So remember that for a series network like this, we want the capacitor to have only small resistance in series. So this is 20, will be 25 ohms for a Q of 2. This will be 25 with 12.5 in series. That will give a Q of 2. This series one is in the normal case, is smaller than the reactance of the capacitor if we're going to have a Q greater than 1. So this will be 25 ohms. That's the step. Now what we do is we look at the what's the equivalent of that if we express it in parallel terms. If this was in a black box, we wouldn't actually know if that was a series resistor or some parallel resistor. We wouldn't know. So I want to find out if it was a parallel combination in a black box, what would we see? What we would see is the same capacitor, which is 25 ohms, but this parallel one, to give a Q of 2, would have to be 50 ohms, because the Q is then resistance over the reactance, which is 2. So that will give us 50 ohms. So you can see the plot is thickening. You can see how we're coming to the answer here, can't you? Remember, I added a capacitor in series with our antenna was a pure 12.5 ohm resistance. I purposely added a capacitor to it. And then what I'm going to do is look at the parallel values that would, if it was in a black box and we considered it as having parallel values, what would they be? So this gives us our final circuit, because the 25 ohm capacitor is actually in parallel. In the parallel case, it would have to be a 50 ohm. It would have to be a 50 ohm. So that's almost done it. These two have almost matched us to a transmitter, but we have got an unwanted capacitance. We can get rid of that. We just put an inductor across it. These two are then a parallel resonant circuit. They've got infinite impedance when they're connected together in parallel. So we just see the 50 ohms for the transmitter. That's it. So our final network, if I can just remind you, we had 12.5 was the antenna. We intentionally put 25 ohms in series of capacitance, and then we found this has got a certain parallel combination which we liked, but to tune out the capacitance, which we purposely put in, we put an inductor. So that gives us 50. So that is an L network. In this case we have a series element and a parallel element. Now you notice that this, when we start with series, we're going from a low resistance to a high one. So on the low resistance side we have a series element, and we step it up to 50 by bringing it to a parallel resonance. So the pi network has to be that way round. It can't be the other way round. It can't match below 50 ohms. So you couldn't get this down to below 12.5 using this network. Yeah, so that's the way around it goes. If you were using, suppose this was 40 ohms, when I calculated the reactance to use, I would have to use that exact formula for Q. Do you remember I said Q squared? We would have to use Q squared plus 1, but this doesn't very often happen. The maximum error you'll get is 2 to 1 error if you ignore that. So very often you'll get a mental arithmetic answer that's pretty close. Now I'd like to talk about the case where we have a very high resistance. For the sake of making the numbers easy, we're going to match that to a transmitter with where we want a resistance of 100. So the first thing you do is find the transformation ratio. To save a lot of writing, I'm going to put transformation ratio. In this case, it's 10,000 over 100, so equals 100. And then we remember Q squared was equal to the transformation ratio. So Q itself will be the square root of that. Q is 10. We've got to use reactances for our network, which give a Q of 10. So the first thing I've done, this is my antenna load 10,000. The first thing I've done, I've purposely put a capacitor across it. And we want the Q, this in effect this capacitor, now should have a Q of 10. So for that to be the case, this very high value resistance across it, the capacitor needs to be a tenth of this 10,000. So it needs to be 1,000 ohms. So then the Q of this capacitor is 10. And now from that we can go on to work our next values. So here's our capacitor, 1000 ohms capacitor. If this is all in a black box, if this is all in a black box, we can look at it either as series or parallel, whichever we wish. We're going to now look at it as series in this case. So if I look at this in the box and I think, well, what series resistance must this have? It's got a Q of 10. In this case, the Q is the reactance divided by the resistance. So, actually I'll write that for you. Q is the reactance over resistance. So it's 1,000 divided by R. Q is 1,000 divided by R. Actually, we know Q is 10. 1,000 divided by R. Which gives us that resistance is actually equal to 1,000 over 10. Oh, sorry, 1,000 over 10. It's 100 ohms. Surprise, surprise, that's what we want. So our overall circuit here, we started off with 10,000 ohms. 10,000. And we intentionally put across it a 1,000 ohm capacitor. And then to get rid of the capacitance from the final result, I had to put an inductor of 1,000. And that gave us a 100 ohm resistance for the transmitter. So you'll notice we end up actually with two networks. It can be either way round. So in this case, this is where we have a high resistance. So we've shunted across. We should put a reactance here in parallel with it to generate the series value that we want, which is then tuned up with the L. So for high to low, this is like the beginning of a parallel circuit, and this is like a series circuit. So high sort of goes parallel to series. The other way around is when it's a low resistance. We put it in series with an intentional reactance, and then we tune it out with what's more or less to make a parallel circuit. So it's like series resonance to parallel resonance. These are the two ways round to it. You can always reverse L and C, doesn't matter. It's more to do with how much capacitor swing have you got available, things like that, or how much do you want harmonic rejection. So that's the L network. Most of these L matching circuits you can do approximately in your head. Usually it's easy matter. So to get it approximately right anyway. So the first thing is just get the transformation ratio. Only look at the resistances. Don't worry about any reactance in the load or anything. So the ratio of the resistances gives you a transformation ratio. Make the ratio greater than 1. And that is equal to Q, the working Q of the thing squared. So the working Q is going to be the square root of this transformation ratio. It's a bit like the turns ratio on a transformer, isn't it? Q is a bit like this turns ratio. Then the next thing is the Q of our components. If it has to be a series component, x over r. If it's a parallel component, r over x. So if you know r, you have to choose an x to give you that q value. If you know r, you've got to choose x to give you that q value. And that's the basis of how it works. That's the L network. Now, just because I know I've got a difficult audience, you're going to say, what if the load isn't a pure resistance? It's got some reactance. So here's a case. That's the one I took before. 12.5 ohms of resistance. It's got 100 ohms of reactance. This antenna's not quite the right length, so it's 100 ohms of inductance. So how do we go? Now remember which L network we're using for matching 12.5. This is going low to high. So these are the two L configurations. This is low to high network. So this is the one we're going to use. So remember we put our 12.5 on this end. I'm going to draw it here. That's where we put our 12.5 on this low end. But it's got a capacitor. Oh, sorry, it's got inductance in it. It's got inductance in it. Just draw that a bit better, actually. Okay, so this is the same circuit. It's 12.5, and I said that this has got 100. Now we wanted, you remember that to match the 12.5 to the 50, we decided before we need a Q of 2. You may remember that. We wanted a Q of 2. So this is the capacitor of our L network we're going to put in. So this capacitor, in conjunction with the reactance of the antenna, gives a single reactance. So 12.5 and some reactance gives a Q of 2. So this reactance we know has got to be 25 to get a Q of 2 with this series. So we want this value to give us a total of 25. So if I put in 125 ohms, these two just deduct from each other, their opposite sign. That gives me the 25. So that I need 125 for my network, and that gives a total of 25. And then eventually, to finish the job, we put this across here, which is 20. Yeah, that's 25. And that will give us our 50 out, the same as I had on the previous example. So we mop up the reactance of the load into the first element of the L network. Now you may remember that there are two types of L network. There's this one for matching high to low, and I'll draw the other one again for you. That's low to high. That's going low to high. So in this case, if I'm going low to high, I want this load. I want it to. I want to know the reactance of it expressed as a series element. So it's a resistance in series with a reactance. So I can mop up the reactance in this. So that's easy. That's what I've just done. In the parallel case, if I've got a very high resistance here, matching high to low, if that's got some series reactance, then for the load alone I must express it as a parallel. I must express the reactance as a parallel element in the way that I've showed you previously with capacitors. Because when we're mopping things up with parallel, we need other things in parallel, so we can use our parallel circuit to do it. So with this load, if the L network starts with a parallel shunt element, then we need to, if the load is reactive, we need to express the load with two parallel X and R, so it can be mopped up with that L. That's what you have to do. Then it gets a little bit more complicated, but that's what you have to do.